This is a lithium battery, and they can be a great source of energy for many projects. The best part about lithium batteries is when they run out of energy, you can simply recharge them. However, this isn't as simple as just connecting them up to a DC power supply. You require a special type of charger, and that's what we're looking at in this video. Most chargers use something called two-stage charging, which, as the name suggests, consists of two stages. The first stage is a constant current stage. The second stage is a constant voltage stage. So what does this look like in practice? During the first stage of charging, the battery voltage increases at a linear rate, as you can see on this graph. However, when the battery reaches about 80%, it will reach its maximum voltage. At this point, the battery charger switches over to constant voltage mode, where it maintains a constant voltage by modulating the current. If we now add the current to this graph, you can see at that point, around 80%, the current drastically decreases and eventually goes to zero when the battery is fully charged. Now that we understand battery charging, let's take a look at some chargers and see how they do it. In this video, we're going to be looking specifically at single-cell USB chargers. They look a little something like this, or if you buy Chinese, a little more like this. But these are quite small and difficult to see what's going on. So with help from my friends at PCBWay, I have made this big one. PCBWay offers a large range of options for projects. For this particular project, I chose to use their PCB assembly option, which you can have for as little as $29. Where a lot of manufacturers get you is the shipping, but PCBWay offers cheap shipping starting from as little as $5.50. Check out PCBWay in the link in the video description. Now, back to battery chargers. These chargers all revolve around a component called an inductor, which is this thing here that looks like a coil of wire. The symbol for an inductor is this squiggly line, which represents the coils of wire in it. However, I don't really see it. An inductor is an electrical component that smooths current by modulating voltage. The formula to calculate this is V equals L di divided by dt, where V is the voltage change, L is the inductance in henries, di is the change in current, and dt is the change in time. The only thing left to do now is build a circuit to do this. In our circuit, we have an input and an output. As we don't need our converter to be isolated, we can connect the negative wires of the input and output together. In this configuration, there are three ways we can connect our inductor. We can connect it across the input or across the output, but we can also connect it between the input and output. Let's now consider how we can build a converter. We need to initially connect our inductor between the input and output. During this stage, the inductor will charge up with current as it tries to stop the current rising. During this stage, the voltage will rise following the leading edge of a sinusoidal curve. Once the inductor charges up, we can disconnect it from the input and connect it to the output. This way, the inductor tries to maintain that current and forces voltage from the negative to the positive. During this stage, the current across the inductor decreases, as does the voltage, which this time follows the falling edge of a sinusoidal waveform. If we repeat this process over and over again very quickly, you can see how we can quite easily get a lower voltage at the output. As long as we don't let the current hit zero, the average voltage will follow a more or less sinusoidal waveform with an average voltage given by the formula Vout equals Vin times time on divided by time off. where time on is the time the inductor is connected to the input, and time off is the time the inductor is disconnected from the input. Now the only thing left is to work out how to turn it on and off. Luckily, we can do this with two electronic switches, by connecting one between the input and the inductor, and the other between the negative and the inductor. For these two switches, we can use MOSFETs. However, we can actually simplify this even further by using a diode in place of the second switch, as it only needs to block current in one direction. While the MOSFET is on, the diode will become reverse biased and it will block current flow. However, when the MOSFET is off, the inductor will draw power through the diode, making it forward biased and allowing current to flow. Now if we take a look at our board, we can see all of these components. The MOSFET is here, the diode is here, and finally our inductor is here. In addition to this board also has two sets of capacitors, one on the input and one on the output. These serve to smooth the voltages and stop any spikes or dips occurring. On the right here we also have some control circuitry to make it slightly easier for me to control it. It's not important for this video, so we can safely ignore it. The only thing left to do now is build a circuit to turn that MOSFET on and off. A lot of chargers nowadays just use a microchip for this, but there is actually a way we can do this with no computers at all, and it revolves around a chip called a comparator. A comparator is an IC that compares two voltages and outputs either a high or low signal based on which one is higher. By using this output to control the MOSFET, we can control the output voltage. But how? Consider this: we connect a voltage that we want on the output to the positive input of our comparator. We then connect the output of our converter to the negative input. When the voltage output is below the voltage we connect and want to have on our output, the converter will turn on and thereby increase the voltage. Once that voltage goes above the voltage we want, the comparator will turn off, and as such the voltage will decrease, and so on and so forth. The cycle will repeat. Okay, so now we understand how to make constant voltage, but how can we make a constant current? We can actually use a very similar trick. If we connect a resistor in series with our converter, there will be a voltage drop over that resistor, correlated to the current according to Ohm's law, which states that voltage equals resistance times current. For example, if we use a 1 ohm resistor, we will have a voltage drop of 1 volt per amp. We can use this in our converter from before, by using this as the input for our comparator instead of the voltage of the output. In this configuration here, by applying 1 volt to the comparator, we get 1 amp of current from our converter. Finally, we can use an AND gate to make sure both these conditions are met before turning the MOSFET on. I hope you found that video interesting and educational. If you did, please consider subscribing. As for me, I'm going to be implementing this into a physical circuit board very shortly. When that's going to be, I don't know. But hopefully I'll see you guys soon, and for now, goodbye.